Hello students, welcome back to another lecture in our course Environmental Modeling and Simulation. Today we are going to continue our discussion on the epidemic model for an infectious disease that spreads with direct contact between a sick and a healthy person. And we discussed in the last class different methods of understanding the mathematical model that we have, a very basic model that was first developed at the beginning of 20th century, and it worked very well for the Bombay plague. I must remind you that now we have much better models to model the diseases that spread, which also account for the differences between the diseases and the way in which they spread. We also look very briefly at what kind of interventions will help us reduce the overall fatalities during an outbreak. Today we are going to continue our discussion and look at the Nullcline method to understand our epidemic model. So let's get started. For revision, this was our model. Dx by dt is equal to minus kxy, where x is the number of healthy people, and I'm going to introduce a symbol for dx by dt. It is x with a dot over it. This is a very commonly used symbol to show derivatives of a variable. And then the rate at which sick people were changing. Here x is, remember, number of healthy people in the population, and dy by dt was kxy minus ly. In the previous lectures, we have discussed at length how this model was derived, what's the logic behind it, and y is the number of sick people. So you can always go back to the old lectures and revise how and why of this model. And the approach we were using was a Nullcline approach. Remember, Nullcline is when the derivatives individually become equal to 0. Obviously, wherever the derivatives intersect, that is where you will have your fixed point. So here we have this symbol, same new symbol for dy by dt, which is y with a dot on top of it. So the Nullcline is basically, x Nullcline is when the derivative of x with time is equal to 0. Since we have not spent a lot of time discussing the Nullcline method of understanding our models, I want to spend some time doing this, especially when we go to 2D bifurcations, 2D nonlinear models. Nullclines are a brilliant way to get started, to understand how the system is flowing before we find out the Jacobian and before we find out the fixed points and understand their behavior and the flow around the fixed points. And y Nullcline would be when the y derivative is equal to 0. So in the last lecture, we discussed how the Nullclines look like, and if x is on the x-axis and y is on the y-axis, then x Nullcline is when minus kxy is equal to 0, which means either x is equal to 0 or y equal to 0. So here you have, had to draw a straight line, and then so these are the two conditions, x is equal to 0, y is equal to 0. I'll use a different color for the y Nullcline. Y Nullcline is when kx minus l, y is equal to 0, which means either x is equal to l by k or y is equal to 0 or both. So when y is equal to 0, we have Nullcline here, and then x is equal to l by k is here. So these are our two Nullclines. Obviously, where the Nullclines intersect, that is where we have our fixed point. But now what we are trying to do is understand the flow of x and y around these Nullclines. Now here's fun thing, the flow around the x Nullcline is always vertical, the flow around y Nullcline is always horizontal. What I want to do right now is look at what's happening around the Nullclines, how the flow looks like. So first let's look at this region. So in this region, both x and y are positive, and x is bigger than L by k. So what we have is that the derivative of x with respect to time is going to be negative, because both x and y are positive, and we know that the derivative of x is equal to minus kxy. X is positive, y is positive, x derivative is negative. Now let's look at y derivative. Now y derivative is kx minus l into y. Y is positive, kx minus l is going to be positive because x is bigger than L by k. Product of two positives, we are going to get positive. So number of the rate at which the healthy people population is changing is negative, number of healthy people is reducing. number of sick people is increasing, dy by dt is positive. So we see that in y-axis direction the movement will be up, in x-axis the movement will be here. So the net flow will look something in this direction. Now let's look at what happens in, and I'm going to use a different color. It's a very light color. Do not worry if you can't see the color. I just want to indicate which part of this face portrait we are looking at. Now here x and y are still positive, but x is less than L by k. So what we have is that the rate at which healthy people are changing is still negative, because there are still some sick people and the healthy people population is going down, but the net rate at which sick people are increasing or decreasing is going to be interesting, because here y is still positive, but kx minus L now becomes negative because x is less than L by k. Remember, this line is x is equal to L by k. So what happens is now we have a y derivative is a product of a minus and a positive factor. So y derivative is also reducing. So net flow is x is going down, x is going towards left, y is going down. So the net flow that we see is in this direction. So this Nullclines, even without finding the Jacobian, even without finding the behavior, the flow around the fixed point, just by looking at the Nullclines and how x and y are behaving around them, we already get an idea of what is happening here. If let's say our initial number, I'm going to use a different color for this. So let's say my x naught is somewhere here, yeah. So my x naught is bigger than L by k, and I'm starting with some initial number of y, some initial number of sick people. So let's say this is my starting point, okay, this black dot here. Now since x naught is more than L by k, if you look at the direction in which the flow is happening, the flow will eventually take me in this direction, which means over time, as time progresses, if my initial number is more than L by k, then according to this model, number of healthy people will go down, number of sick people will go up, y is increasing and x is reducing. However, so this is x naught 1. If I am starting somewhere here, x naught 2, let's say here in this black position, this black dot here in this particular area, then x naught is negative, so number of healthy people is going to go down. Number of sick people is also going to go down because dy by dt is negative. The net flow is going to be in this direction. So what I'm going to notice is that the disease does not spread, it starts going down, the disease starts diminishing. So now try to understand what's happening. Let's say a disease started, but now it is not spreading. It's more people are not, dy by dt is not positive. We have some sick people, they are recovering, some of them are not recovering, and some new healthy people, some earlier healthier people are getting sick. But overall dy by dt is negative. We can say now the outbreak is diminishing. We are getting rid of this disease, this outbreak. So if x naught is more than L by k or x is more than L by k at any time, then even the healthy people number starts going down because dx by dt is negative, which is the case of all outbreaks, but dy by dt is positive. So the rate at which the sick people are changing is positive. So we see that more and more people are net falling sick, which means the disease is spreading. Now x is equal to L by k is the boundary of deciding whether it's a self-limiting outbreak or it's an outbreak that's going to spread. So briefly, what we have is on the left side of x equal to L by k, we have an outbreak which self-limits. So basically it does not spread, we have some fatalities, some people recover, the disease goes away, which is, for example, what happened in Kerala when the Nipah virus outbreak happened. So it's an outbreak, it is not an epidemic. X more than L by k, this is where now we are entering the zone of epidemic. So epidemic, more and more people are falling sick, number of sick people is increasing with time, the disease is spreading. So you can see that even without finding the Jacobian, we already know the importance of this L by k term. This will determine how the disease spreads. Now let's look at L by k. L is the rate at which people are dying, fatality rate. And the k is the rate at which interactions between healthy and sick people end up with healthy people turning sick. So infectivity. Now L by k is constant for any disease. So for a disease, we discussed this in the last class and it's also a good time to revisit now. For a disease that has a high fatality rate and a low infectivity rate, what's going to happen is that this boundary of L by K is going to be very high. So we need a lot of people to be infected with a very fatal dangerous disease that has low infectivity. So it doesn't spread very rapidly, but it almost always kills. We need a lot of people for it. We need a lot of people, initial people, to be sick for it to enter the epidemic phase. Otherwise, most likely it's going to be outbreak. So basically, diseases that have high fatality, low infectivity, they have a higher L by K value. So we are more likely, if depending upon number of sick people at any given time or number of initial healthy people at any given time, we are more likely to enter the outbreak because the L by K ratio is very high. Now, for diseases that have low fatality rate, high infectivity, like the viral disease that caused a pandemic, L by K is very low. So almost always, like let's say this is L by K for a disease 1 and here is L by K for disease 2. So it will take very little initial number of sick people for this to blow into an epidemic. It will take a large number of initially sick people or initially for this disease to break out. Okay. So this was our epidemic model. Now, how do we improve this model for other diseases? This is for a disease like the Bombay plague, where direct contact is required. The symptoms appear pretty quickly. There is no waiting time between the not very big waiting time between initial exposure, and then the onset of symptoms. And we sort of, it's a very simple model, but how can we improve it? I have already shared with you how to incorporate for immunity, that a natural immunity that develops in recovered people in case of certain diseases, but does not develop in case of certain other diseases. The other thing we can do is look at the diseases where there is a time lag. Now, when I go to the practical portion of this course and I teach you how to incorporate time lag in the models, we will actually look at HIV model, how HIV spreads in the body, not in the community, but in the body, and how it takes over our T cells and it can eventually end up with full-blown AIDS, and how different interventions like antiviral drugs can actually reduce. Even though it's a medical model, it works really well for certain environmental situations. And the reason why this model is important is because there's a time lag between infection with HIV and onset of AIDS. Now, if in an environmental system, we have a time lag between the actual triggering event and the catastrophe that follows, which is very often the case. For example, we have been accumulating greenhouse gases for many decades now, centuries now, since the onset of the Industrial Revolution, when we started using coal-fired boilers to run our engines. And the catastrophic effects of climate crisis have only recently become significant enough for us to worry a lot about them, and we should worry about them. So now here you see there is a significant time lag between the initial beginning of the problem and then the effect of the problem. That is where our focus is. Now in that case, we need to change these models to incorporate for the time factor. Notice none of these functions. So we have dx by dt is a function of x and y, and dy by dt is a function of x and y, different function. So time is not important here, and even though time may not be important, we may have so we don't want time to factor in here, because if time factors in here, then this becomes very complicated. So we don't need time to be here, but we need to account for the time lag del t, and that's one of the ways in which we can show, and I'll go about it more in detail when we do the practical portion of this course, which will be towards the end of the lectures. I also want to revisit now another model that we had studied before, Lotka-Volterra predator-prey model. And I want to show you one of the limitations of that model and then move on to limit cycles, how the model should be versus how the model is, and what kind of limit cycles there are, how they look like, and why they are important. Okay, so let's revisit Lotka-Volterra predator-prey model. Okay, so Lotka-Volterra predator-prey model, we have two animals, one of them is a predator, fox, and one of them is a prey. In our case, the predator is going to be the fox and the prey is going to be the rabbit. So let's write down the model. So dr by dt, which is the rate at which the rabbit population is changing, we decided looks like this. AR minus B RF, and the rate at which foxes are changing looks like this, minus CF plus DRF. Very quickly, let's try to understand this model before we go ahead and I show you the limitations of this model. Very quickly, you can see that the rabbits, if there are no foxes, they are going to multiply, because this is not a logistic model. This is the growth factor is not logistic, it's exponential to make life easy right now. And actually, there's an assumption, a very big assumption. So if there are no foxes, so if there are no foxes, this becomes 0, this becomes 0, this becomes 0. So all we have is dr by dt is equal to AR. So rabbits are going to exponentially grow, which we know will mean that in limited time we have very big number of rabbits, something that our ecosystem will not be able, that particular limited ecosystem will not be able to contain. So that is a limitation of this model. But there is an assumption here. The assumption is that because foxes are not 0, foxes will not allow the rabbits to grow exponentially without being hunted down. So it is not the resource limitation that is controlling the population of rabbits, it is the predation by foxes that is controlling the number of foxes. So very important thing to note down in this version of predator-prey model, that it is a predation that controls for a rabbit population. And not the resource limitation. Basically, the foxes will not let the rabbits increase to a number where resource get limited, not resource limitation. Okay, so what I want to do is I want to look at this model and show you how the face portrait looks like. Now, to make life easy, we should non-dimensionalize this model, which means we should get rid of all the dimensional systems here. Rabbits multiply really fast, foxes take time, young ones take time to grow up, become mature, to produce their own young ones. So they are operating at different time scales, so very important. And we may have a lot of rabbits, few foxes. So again, that scale of numbers of rabbit and foxes may not be comparable, so very important to non-dimensionalize it. So very quickly, let's go ahead and non-dimensionalize this system. So let us define a new, let's look at the units first. On left hand side, the unit is number by time, and on right hand side, it also should be number by time. So we have number here. So clearly the unit of A is per time, the unit of per time, and here the unit is per time, per number, and here we have number. Similarly, C and F will have units comparable to A and B. Okay, so when you're trying to non-dimensionalize this, we definitely want to get rid of numbers, and we also number the unit number and also the unit time. So we definitely want to get rid of the time unit, and we want to get rid of the number unit. Here we have number, here we have time, and same thing is true with the second equation. When you non-dimensionalize the system, what you will get is something that looks like this. dx by dt is equal to x minus xy. dy by dt is equal to mu y into x minus 1. Okay, so this is the model that will come. So this is something for you to try again yourself, and if you have any issues, you can ask us in the comment. You can ask us in the platform, and our TAs will help you how to non-dimensionalize this system. But please do not forget to try non-dimensionalizing this. I can assure you that this is important, and for your exam perspective to non-dimensionalize, learn how to non-dimensionalize models. Okay. So now we have the system, we can write the Jacobian very easily. So I don't want to go the Nullcline way because I want to show something to you. I want to show the face portrait, and the Nullcline way will show me the flow, but face portrait Jacobian is better. So if I try to find the Jacobian of this, what I get is okay. Now let's look at the fixed points, because after Jacobian we want to find a characteristic equation. So the fixed point, one of them very clearly is that both x and y are equal to 0, 0. Let's look at another possibility. What if x is not equal to 0 if x is not equal to 0, then for the first equation to be equal to 0, y needs to be equal to 1. How? So very quickly, what we have here is dx by dt is equal to x into 1 minus y. For this to be 0 when x is not equal to 0, y needs to be equal to 1. So we can put this information here. If y is equal to 1, then x also needs to be equal to 1. Why? Because we have mu into 1, x minus 1 equal to 0. Assuming that mu is not 0, x has to be equal to 1. So the next fixed point is 1, 1. So I'm going to not focus very much on x, y equal to 0, 0 fixed point. And the simple reason is this is a fixed point with no foxes, no rabbits, which is not of interest to me. I'm interested in an ecosystem where rabbits and foxes are both present. So to save time, let's just look at J11. So what we are going to do is, if you remember, to understand characteristic equation at this particular fixed point, we are going to put the values in a Jacobian. So what we get is 0 minus 1 mu 0. Here trace is 0 and delta is positive. We are dealing with the center, right? So how the phase portrait will look like is x is here, y is here, non-dimensionalized system. So 1, 1 does not mean we have equal number of rabbits and foxes. 1, 1 is non-dimensionalized system, 1 unit of rabbit, 1 unit of fox. And the unit may be different for both of them, but they are non-dimensionalized. So this is the center. So basically we have an endless array of circles around this. So basically, let's say if we start with some number of foxes, I'm going to use a different color. So let's say I start with some number of foxes and some number of rabbits, then basically the population over time is going to flow in this circle. If I choose this number of foxes and rabbits, the population over time is going to flow in the circle with the center at 1, 1. Now there is a big problem with that. We know this in biology that this is not how it happens. We can't have 100 units of rabbits and foxes living and moving around in circles. And we know logically also it won't happen, because there will come a time when one of them will become negative, which means that species has gone extinct. Circle would not work. And we know from biological information, this is not what happens. In an ecosystem, the herbivore and carnivore population cannot be as big as possible. Even if we have more herbivores and carnivores to begin with, over time they dwindle and they circle around a limit cycle, which brings me to the next topic that we are going to cover, which is the limit cycle. So let's very quickly understand how this should look like based upon what we know from our observations in the actual ecosystem. This is how it looks like according to our model, right? Circles around circles, because 1, 1 is the center. How it should look like is something very different. So we have x here, y here, and this is 1, 1. Now let's say we have this circle. If our initial point is somewhere here, then we know that the rabbit and population of foxes changes according to the movement around circles. Sometimes there are more rabbits than what we see. Sometimes rabbit population goes up, sometimes foxes go up, but they move around in the circle. Here, for example, we'll have highest amount of foxes throughout the cycle, and then when we come here, we'll have lowest amount of foxes. Here we have lowest amount of rabbits, highest amount of rabbits. This is also very similar to what we see in weather cycles. There are weather cycles, seasonal cycles, and other oscillations that happen in our environment, in our own body. For example, our heartbeat. There's a typical cycle in which our heart beats during our day. But there are disturbances. Sometimes the heart rate will go up. Sometimes the number of foxes will go up. So let's say number of foxes goes up here, right? So earlier they were here. We were on the circle. We were moving in the circle, but then the foxes went up. Now what will happen? According to our mathematical model, Lotka-Volterra, it will move in a new circle, but that's going to be very difficult. Now the whole ecosystem has been ruined, and that's not what we see in our environment. In our case of our body, let's say an event happens that triggers our heart rate to go up, and our heart rate goes up. It doesn't mean now our heart will beat in the new circle with increased heart rate. That's not what happens. What happens is it comes back to its normal. It comes back to its baseline. So what we see actually in environment is not what this model predicts. So This is what the model predicts. Let's see what we actually see in the environment and in our real life. What we see in the real life looks something like this. So let's say we have x here and we have y here, and this is 1 1, and this is let's say our original circle, because 1 1 is the center, and if foxes are, let's say foxes and rabbit begin here, they go around in the circle. There are times when the fox population will be very high, which will be somewhere here, and then times where the fox population hits its minima, which will be here. Rabbit population hits its minima, rabbit population hits its maxima, but they go around in circles. This is also what we see in many important environmental oscillations, environmental cycles, like seasonal cycles. We know that seasonally values of different environmental parameters go up and down, and together they have some kind of oscillation that happens. And sometimes some season the BOD might be higher naturally, some season it might be low naturally without human impact, that is. But then they stay in the rhythm, so we expect them to stay in the circle, not to go out of the circle. However, then there are incidences or accidents or instances where the number jumps off. Let's say suddenly we have more rabbits or less rabbits, because this circle is big. So let's say suddenly the number of rabbits goes down. So initially we were here going around in the circle, number of rabbit falls down to here. According to our mathematical model, now the rabbits, now we'll have a new circle around 1 1. So now, since initially the rabbits died down, the foxes will die down, and now we will never go back to the old abundance. The blue circle will stay in the red circle. But what we see in the environment is very different. What we see in the environment is something like this. Once rabbits go down, eventually they come back. Because of the resilience, they reach back to the old circle. So instead of going around in circles around the center, what we have is a system that looks something like this. So we have a cycle, natural cycle. Any aberration will bring back. Let's say here is, from here the aberration took us here, it will come back to the circle. It will come back to the old cycle. For example, in case of seasonal cycles, let's say one time we have a hurricane and that disrupts the rainfall pattern, that disrupts the movement of winds. But then again, I'm talking about without human impact. The seasons, the weather, it balances itself, returns back to its old rhythm. This is also very important for other oscillations that we see in our mechanical engineering, we see in our biology. For example, with our heart. Our heart has an oscillatory rhythm to it, the way so there's a center and there's a circle around in which the heart follows its pumping pattern. If there is any instance during the day when the heart rate increases or decreases for some reason, so let's say the heart rate increases, or in this case the number of foxes increase for some reason, like foxes from another forest come and migrate into this forest. Eventually what happens is that after moving around, they eventually come back to the old circle, the old pattern, the old. So this is what we'll see. So any aberrations around this center, this orbit, will eventually end up on the orbit. This is what we see in heartbeat. This is what we see when we have some really dangerous oscillations, natural oscillations in bridges, in the wings of the airplane. They don't just vibrate more, the oscillations don't get more extreme, entering into a new circular orbit with the same center. Instead, they return back to the old oscillation pattern. So this shows you a very different style of what is happening. Until now, I had told you about spiraling in, spiraling out around fixed points, spiraling in around fixed points, and then having centers, right? So here we have a center, things are spiraling out, which means we have both real and imaginary portion to our eigenvalues, and the real one is positive, so it's spiraling out. Here we have real and imaginary, the real one is negative, so it's spiraling in, and here we have a purely imaginary eigenvalue, so things are circling around, which is the case with Lotka-Volterra predator-prey model. What I'm introducing to you now is a very different concept. What it is saying is that we have one orbit. It's different from case of a center, pure center. But here also it may have a center. Now the flow lines around the center are like this. They are just an endless array of circles. So this is how a center looks like. In case of a limit cycle, which is a new concept that I'm introducing you to, we have an orbit. We don't call it circle. It can be any shape. We have an orbit. There is flow going around the orbit. If there's any aberration, let's say we move here, we start from here, we are not starting at the orbit, few things may happen. In case of the flow may look like this, eventually join the orbit. If you're starting inside, the flow may eventually join the orbit. So this is a case of a limit cycle that is stable. But what you need to understand is, in limit cycle, we have one orbit, only one orbit. We don't have an endless array of circles around each other. That's limit cycle. In the next class, I'll talk to you about what limit cycles are, and we have stable, unstable, semi-stable, half unstable limit cycles, and we look at 2 examples of limit cycles. That's all for today in this lecture. See you in the next lecture. Thank you.